operate. Right, stay. So this is kind of related to that global temperature rising problem. So let's say this. Let's say I have a mean of 16, standard deviation of 1.5. So again, sorry? We're sort of getting into chapter 8. So this is going to lead into chapter 8. Yeah. So if I take a sample of, let me tell you, let's say this is, no, screw it. If I take a sample of 33, what can you tell me about the new picture of all the means of all the samples of size 33? Yeah, like we just said, it's going to be normally enough, approximately normal. So the central limit here says that it will be approximately normal. I like to call it normal enough because it's normally enough to use the z-score chart. All right. Okay, stop there for a second. So everybody decent with where this is? Okay, I haven't done anything yet, so hopefully we're all right. And then I ask you, can somebody help me figure out between what two scores would I find 98% of the data? Between what two means, what two sample means, would I find 98% of the data? What does that mean? Hopefully that sounds familiar. It sounds very much like the problem somebody just asked me about, the middle something other percent, right? So I want to find the middle 98%. You could be a lot more specific, can't you? Everybody got their z-score chart back? Right, so how do I figure this out? What area is out here? 2%. So what area is down there? 1%. So look up 0.01, see what z-score that is. Be more specific. 2.33 is. So negative 2.33. So this one has to be. Why must this one be positive 2.33? Symmetric. I love it. Because towards the end of the semester, we're going to be working with a different distribution that's not symmetric. So we're actually have to look both of these up separately. They won't be one the negative of the other because it won't be symmetric. So right now, thank God, we got a normal curve, symmetric. I look one up, I got the other one automatically. All right, how are we doing so far? Is everybody with me right now? Because all I'm going to do then, I'm going to give you a set of ways. I'm going to change this. And then you have to look up the right z-score for that. And now what will be the next? What's the next step? Because these are, what are these again? These are z-scores. And I want to know what x scores correspond. Let's say this is, I don't know, age in years. So I want to know what years represent the middle 98%.
Multiplying by the standard deviation and add the...
Yeah. Because what does this mean by itself? Negative 2.33, that means that that answer is 2.33 standard deviations below the mean. So I would take, to get this x score, I would take the mean minus 2.33 standard deviations, right? So I'm using this formula, but you don't even have to look at it like a formula. What does this mean? It's that many standard deviations below the mean. So I take the mean and I go down this many standard deviations. And you don't have to look at it like a formula. It's just the idea of a z-score. If you like formulas, like hopefully then you can just plug and chug, right? So I want to go down 2.33 and up 2.33. So really I can kind of capture this by saying I want to go up and down 2.33 standard deviations, right? Is that cool? And I can write it concisely because it's symmetric. You know, I have two different numbers. The same number, just one's negative, one's positive. All right. Maybe. Now, I'm not being careful enough here, though. What have I not written correctly? What should be here? Because I'm talking about 33 things, right? So what do I need to use here instead of sigma? What has to happen? Because I took a sample. Change the standard deviation, so it should be sigma over square root of n. And now we can throw in what the mean and the standard deviation is, right? We know what the mean is, 16, minus 2.33 times 1.5 divided by the square root of 33.
15.391.
Who's it?
15.392.
So this one will be 16 point, what would it reach out for you? What you got? 608, I think. Yeah. Because it's symmetric. So the amount that I went down from 16 is the amount that I'm going to go up from 16. So I'd say between 15.392 years and 16.608 years catches 98% of the people. 98% of the people are between those two. That's what that means physically in the real world. Sorry, I went kind of low. So all the work we just did is old work. So what Chapter 8 does is it takes the work we've already done and it just kind of reformulates it a little bit. And one extra little thing it does. All right, so what we've effectively done is we've taken this formula here that we've known forever, right? That formula right there. And we adjusted it a little bit. I need to hire somebody. So what do we do now? We said, okay, so we made it like this, up or down, this many of the new standard deviations. We stopped it for a second. Is that cool? I mean, that's all we did. I don't want to use the one for individuals because I'm taking a sample, so I got to change that standard deviation. And to be a little more honest, it should be like that. I'm looking at sample means now, right? Okay. Every time I teach this, I do it a little bit different, so I'm going to catch up with myself. So here's the last step. This is all old news. Here's the new news. Here's the only new thing to this. And we do this in steps because I want you to get used to the first change, and then there's going to be another change that makes it more realistic. Because in reality, when I'm doing statistics, when I'm going out and analyzing something, do we know what mu is? Right? No, we normally don't know. And actually, we normally don't know what sigma is either, do we? No, we normally don't. Right? But the first step we take... All right, let me see if I can make this make sense. So what we change is we normally don't know mu. We don't know mu. So what can we use instead? If we don't know mu, what do we use instead? What's the next best thing? And that's a weird question to ask, but what am I doing? I'm taking a sample. So when I take a sample, I can calculate the sample mean. If I don't know the population mean, what's the next best thing? Sample mean. I like it. So if I chose my sample nice and randomly, and I take the sample mean, that sample mean should be close to the real mean. So that's why I use it when I don't have mu. I use that. So I'm going to use the exact same formula, except I'm going to put x bar instead of mu. And now the idea is, now here's the whole idea. So when we calculated that 98% interval that we did earlier, from 15 point whatever up to 16 point whatever, I could say this. I would be 98% confident that any specific score would be in there. Does that make sense if I say that? Because how much of the data did I catch? 98%. So how certain are you that a certain data value was in there? 98% sure. right? If you wanted to be more sure, you would just go out a little more, wouldn't you? Because at 99%, the z-score would have been further out. Does that make sense? So you cast a wider net if you want to be sure you catch a certain fish. I don't even like fish, but I like that analogy, right? 98% thing, I have to cast out this big. If I want 99%, I have to cast out a little bit bigger. If I want 90%, I cast a little tiny net. It's a 10% chance that I don't catch my fish because there's 90% of the fish are in there. I don't know if that analogy makes sense. Some of you guys don't like fish at all, like me, but I've worked through it. Okay. So here's a. Oh, I did heights on this thing, but here's a. Let's do IQ scores. Just to show you that in real life, we do sometimes already know the standard deviation. So I really want this to make real life physical sense. So let's say that. So IQ scores we know. We know that they're normally distributed with a standard deviation I think is 16. I think some books say 15. I can't remember what this one says. And the mean of everybody happens to be 100. So if you know your IQ score, you can actually calculate your z-score and see where you are, right? Or Forrest Gump was kind of far down. He had other things going for him. So what I'm interested in is, what if somebody claimed that there's a little tiny section of some state where they have higher IQ scores? So the first thing I'm going to do is I'm going to go test that claim. I'm going to see, are their IQ scores higher or lower or what? So what I'm going to do then is I'm going to say, okay, I want to catch the middle. Let's say I want to be, how do I want to say this? Oh, I got it. So I go down and I take a sample of, let's say, 48 people. So take a sample of 48 people. And I want to know their average. I want to know, so let's say I'm in some, let's see, what's somebody's favorite state? Good Lord. Everybody said something at once. Washington. All right. So let's say up in Washington. Oh, I don't want to show off, but here's Washington. No, it's more like Oregon. Washington got more interesting, but we'll see. And there's a claim that these people right here in this section of Washington have higher IQ scores for some reason, right? The next step of this study would be, what are they eating? What are they drinking? What are they doing? What's happening, right? To maybe make their IQ scores higher. So the first thing I do, though, is go just see what's going on there. And I go there and I take a sample of 48 people from that area. Are you guys with me? If I take a sample of 48, and why do I do that? Because there might be now this section of Washington actually doesn't have a lot of people, but let's say there's a lot of people living there. Do I have time to talk to everybody? No, that's why in statistics we take a sample. So I'm going to get, from this sample, I'm going to get a mean in X bar. And let's say X bar is 105. You guys kind of with me? Little tiny bit? Little tiny bit? Is that more than the national average? Yes. So the whole question really becomes, is it more than that enough? Right? So one way to test that, and these exist for a different reason, but one way to test that is to create what we call a confidence interval. Now somebody help me out. What's the real average IQ score of the people in this region? The correct answer is, I don't know. Right? We don't know. In fact, our best guess is 105. But is that, now I really want you to understand, 105 is bigger than 100. Why can't I just stop and say, oh yes, that region, something's weird going on?
It might not be.
Because the actual mean might not be more than 100. Maybe I just happened to pick 48 people that were slightly higher IQ. You guys understand what's going on here? So it's not good enough just to stop. If I have a sample mean, I can't trust that. I trust it more if my sample size is bigger and bigger, of course. So that plays in. But I don't trust it on its own. So what I'm going to do is I'm going to say, I want to go out so far from 105, and I want to try to catch the real mean. So that's the idea. So this is the sample mean. Now, the real mean is somewhere. So if I take a sample mean, and I go up and down, and it catches it has a good chance to catch the real mean. Let me make sure. All right, good. You guys are sort of with me. It's weird to try to figure out how to say this because we haven't gotten enough into it for me to say some certain things. All right. So I get to pick how confident I want to be. There's always, the beautiful thing about stats, the thing that people don't understand and the reason they hate stats is because there's always a chance you're wrong. But that to me is the beautiful thing. It's the most honest form of math. It says, give or take. I don't know. There's a 1% chance I'm wrong, and that's better than normal, so I'm okay with that, right? You guys kind of understand? And real quick, what we're building up to, anybody at all paying attention to politics right now? Anybody understand the presidential elections coming up? Have you guys ever seen the polls? Polls always say stuff like Bernie is 44% and Hillary is 47%, so Hillary's going to win, when at the bottom of the screen it says plus or minus 4%. Oh shit, so they could be the same, right? And why is there a little freaking plus or minus 4%? Because how did they get those percentages?
Sample.
They talked to a freaking sample, so they got to cover their ass. And where's that plus or minus 4% come from? Holy shit, that part of the equation, right? Now, we're not to the point where we're doing percentages yet. We're still doing means. But that's the part of the equation that it comes from. And how do you make that error, the amount that you think you're off by, smaller and smaller? You make your n bigger and bigger. That only makes sense. The bigger your sample, the smaller this give or take is going to be. It's nice how it all comes together, maybe. Some of you are still like, finish this and just let me see what happens. Okay. All right, so let's see. Where am I at? Okay, so I got a mean. Now, I know this is true. This is true for who? Everybody. So is it true for the people in this region? Yes. So that's why it's not, it makes sense that I normally don't know the mu. I normally don't know the mean of something. But I could know the standard deviation. So in this case, I do know the standard deviation for everybody, so that's the standard deviation for them, but I don't know their mean. Of course I don't know their mean, right? I know everybody's mean, I don't know their mean. All right, so it makes sense that sometimes I can know this, but not know mu. I like it. Okay, maybe. So what we're trying to do now is using our best guess. Can I say with 90-something% confidence that the real mean is between this and this? Or I'll say it even better here in a minute, because semantics is important. All right. So let's say I want to be, let's use 98 because we just did it. We want to be, let's say we want to find the 98% confidence interval. For the true mean IQ of this region of Washington. Of this region. That's a lot of writing for me. Sorry, buddy. Good luck. We want to find a 98% confidence interval for the true mean IQ of this region. Because what do we have right now? A sample mean IQ. So I want to start from there and go out so much, catch 98% of the data, and we know how far we got to go already. How far do we have to go? 2.33. We just did the work, right? We just did a 98% a second ago. So that's what I mean. That's the old idea that we used before already, but it's being used in a different kind of way. This is what's meant by the difference between descriptive statistics. I calculated that. And inferential statistics. What can you say about the whole population? In this case, the whole population of that region. Right? I want to use what I see to extrapolate about what I didn't see, which is namely everybody else in that region, right? So, how does this work nuts and bolts, Jeff? Stop talking huge. Just talk about how does this work nuts and bolts. So the mean was 105. The population standard deviation was 16. And I want the 98% confidence interval, which means the z-score is 2.33. Now I know it's plus minus, but that's in the formula. The formula is your sample mean, give or take this many standard deviations. See, the plus or minus is already in there. You guys see that? That catches the fact that you go down and up. It's already in there. All you care about is what the number is. I like it. So now you just got to plug and chug. That's the beauty of this. It takes me forever to explain something, but then almost always we end up with just plug stuff in the right place, right? So what's the sample mean we got? Was 105. Give or take 2.33, so we catch 98%. Standard deviation, so that'll be 16 divided by the square root of what? 48, good, because did I erase it? 48 people. Roughly. So what I normally do is I calculate this first, and then I can add that to 105, subtract it from 105, right? There's no plus or minus button in your calculator. Don't ask me. I did have somebody ask me that once. Jeff, where's the plus or minus key in my calculator? I don't know. There isn't one. Shit. And incredibly enough, what we call this piece of this, we call this the error. Why does that make sense? Because it's how much I think I'm off. 105, give or take this much, is how much we think we're off by. So we call this the error. Error. So let me rewrite that up here higher so you guys can all see what's going on. So has anybody got that for me yet, the error?
5.3814.
So 105, sorry, 5.381.
381.
Cool, I like it. Normally, for this number, I say go one more decimal place than this number. All right, whatever the mean that they gave you, or whatever the mean is you calculate. So I could say 105, give or take 5.4. Is that cool? You guys see that? But if you ever round further out, you're more accurate, so who cares? But at least one more decimal place than what this is. So now just add that. So it's from,
110.
yeah, if you add it, you get 110.4. You subtract it, you get
99.6.
99.6. Now, this is beautiful. I can't take credit for this because I just made numbers up. But let me see if you guys can see this. So how certain are we that we caught the real mean? How certain are we that this interval catches the real mean? All right, so let me do this right now before we interpret what we just saw. You're going to love this part of it, right? There's the math part of stats, and then there's the interpretation part of stats. You have to write a statement about what you just did. So here's the statement. You guys are like, oh yes, Jeff, you're making stats even better. Here's what it sounds like. We are how confident? 98% confident. Now real quick, don't write this down. I don't want to say that the real mean falls in this interval, because the real mean isn't like whoa, no, the real mean is somewhere. So I say I'm 98% confident that the interval I made, this interval, catches the real mean, because the real mean is in one place. It's the interval. If somebody else went and did 48 people, are they going to get the same mean I did?
No.
Are they going to get the same confidence interval I did? No. So there's a 98% chance that any confidence interval you make will catch the real mean. So what chance is there that it won't catch it? 2%. So if 100 people went to Washington and took 48 people, I erased Washington, I'm sorry, Washington, and take 48 people from that region, how many of them would not catch the real mean? 2 of them. I like it. Beautiful. On average, right? Not exactly 2. Right. Sure, like Shaquille O'Neal taking free throws. I don't know, but I can say on average about 2. Do you guys understand that a little bit? I'm gonna continue to say something like that every time we do a problem until it really, really sinks in. Okay, so we're 98% confident that the interval 99.6 to 110.4 contains the true mean IQ for people in this region. Blah, blah, blah. All right, now somebody help me out. What was the claim that somebody made? The claim that the IQ of people in this region was higher than the regular IQ of everybody. And the regular IQ of everybody was 100. Is that evidence? Let me see if you guys get this. Why is it not evidence that it is higher? Because could the mean of this region of Washington be 100? Yes, it's in there. So if I wanted evidence that was more than 100, my confidence interval should have been not contain all above 100. That would mean the mean would, with 98% confidence, be above 100. So I'd say, I am 98% confident that the mean is higher. But here, I can't say that. Shit, this doesn't prove that statement. I really want you. I went a little further than we actually have to at the moment, but I don't care. This is the perfect place to say that. So you could use confidence intervals to get a feel for if a claim is true or not. To really test a claim, we do something called a hypothesis test, which is still in our future. But you can actually use confidence intervals for this. Maybe. All right. Whew. So, let's do another one. Let's see. Yeah, let's do one more, and then I got a little handout like I always do. Somebody keep an eye on the time for me. Is it 12? What is it?
11:30.
11:30. Thank you, honest people. All right. Let's do one more quick one here, and then I'm going to let you try out this handout. I can't remember if I put... Oh, yeah, I did. Shoot. Oh, well. So let's say it's known that sigma is 7.8. We take a sample of 212 people and find a sample mean of what you got? You can do it, buddy. 81. Okay. I'm not feeling creative also. I don't know what these mean. You can come up with your own interpretation. So is everybody with me? What's happening? Yes?
7.8 or
7.8. Cool. It's pretty cool so far. Nothing has happened yet. So took a sample. I happen to know that this is true. And we just saw a second ago a situation where that could happen. We know what the standard deviation is. So we go take a sample of 212 people and we find that the mean whatever is 81. The mean golf score. I don't know. I don't even play golf. I don't eat fish. I don't play golf. But those are my go-tos. Find the 99% confidence interval for the true mean. Alright, so let's do this one together. So I'm going to do this the long way, and then I'm going to point out the short way. So what would this look like? Confidence intervals always catch the middle, right? And that's why we're able to do everything we can. So I want to go out so far that I catch 99%. So how much is out here then?
25.
Yeah, 1% total out, so it's 5%, 0.5%. What is that as a decimal? 0.005. I like it. Stop there for a second. So if you look up 0.005, yeah, it's an asterisk, right? And it leads you down to 2575. This is right in between 257 and 258. Does everybody see that on your z-score charts? All right. Now let me point something else out. Do you guys see? I'm trying to stay away from turning this thing on. If you look on the negative side, look at the bottom. No, not there. Here. Positive side. This is what I call the little baby z-score chart down here. Do you guys see where it says confidence level? Holy shit, that sounds like what we're talking about. So for a confidence level of 0.99, what z-score do they get? That's what they call the critical value. Holy shit, well we just got it. All right. But do they have 98% in that little baby chart? No. So you got to know how to do it that way, but I will sometimes ask you, these are the most often used ones. 95% is the most used one. That's what Gallup always uses, is the 95%. And why does that make sense? Because then out here would be unusual. It goes out 2 standard deviations. You guys semi with me, or roughly 2, 1.96. All right, so what the hell just happened? I'm trying to create a confidence interval, so I know I'm using this formula here. I'm given this, I'm given this, I'm given this. I got to figure out what that is, and we just did. We got 2575. So now I just plug and chug. Now I just plug in what I know. So this would be 81, give or take, 2.575 of the new standard deviations.
7.8. Cover the 200.
212. One and a half. 1.3. There. So do this piece first. Do the error first. Really? Sorry. I don't know. You guys understand what I just did? Huh. It's better than normal. So 1.38, so you can make it like 1.4, be one more decimal place than that. You guys with me? Or if you make it 1.38, that's still even better. So just don't round too much. That's the thing to get. So now I just got to say 81, give or take 1.4. Make my interval. So if I subtract it from 81, what do I get? 79.6. Then I add it to 81, 82.4.